How is everybody? It's Friday. Nice to start your week off with a Thursday, right? Today's Friday, yesterday must have been Thursday. Okay, who'd like to start us off with a prayer today? Go ahead.
Our Heavenly Father, we thank you for this day. We thank you for the opportunities we have to be here together to learn and to develop ourselves. Father, we pray this time that we might be able. Father, please bless those that are traveling this time and those that will be traveling soon to be able to do so in safety. Help us to have gratitude in our hearts for all the blessings that we have. This wonderful university, being able to learn, and also the many blessings that we enjoy with our families and the gospel. Father, we love you and we pray for these things in the name of Jesus Christ.
Amen. Thank you. Is Caleb Meyer here? Come on up, Caleb. All right. We had quite a... did you guys hear about the cross-country teams? I didn't even hear about this until today. It was like a week ago. The men's cross-country team won the national championship. Yeah. And they're like... That's not Caleb. Then the women's team took second. The men's team has taken second before, a couple times, but this is the first time they have ever won the national championship. So Caleb, come on over here. Another team also won a national championship. Which team do you play for, Caleb?
Soccer, men's soccer team.
You have the men's soccer team won the club national championship. And Caleb's one of our own here. So what position do you play?
Center mid.
Center mid. So the center of it all, huh?
Yep.
And what? Extra credit? Yeah. Extra credit for anyone that wins a national championship. We have high standards here. So how long have you been playing on the BYU team?
This is my first year.
First year? Did you start?
No.
No start. And where was the competition at?
It was in Round Rock, Texas.
Round Rock, Texas.
Right
Tell us some of the teams you guys beat.
We started off tying Texas A&M, which was kind of sad because I know most of the people there.
Are you from Texas?
Yes, I am. And then we played University of Delaware. We beat them like 5-0 or something like that. It was pretty bad. We played University of North Carolina. We beat them 3-0. We played Ohio State in the final. And we actually went down 1-0 at first, but we came back to 1-3 to 1. We gave them a little bit of hope. We had to come back in there.
I always love to see Ohio State lose.
Absolutely.
So, great. Well, let's hear it for Caleb. Nice job. Okay. So, the BYU men's soccer team was the very first college team to ever be a franchise. Do you guys know that? So, maybe 20 years ago, close to 20 years ago, the BYU men's soccer team, they were a club and they would win, like they always win the national championship. But they couldn't go NCAA because of Title IX stuff. So they bought a franchise. BYU bought a franchise, and the BYU team played at a level considered higher than NCAA level. And they did that up until 3 years ago. I don't know why they came back down. But now they're back to club. They've only lost one game since coming back to club, which was to Florida last year in the national championship. So, yeah, they're pretty dominant, pretty amazing. So, nice job, Caleb. So, okay. One of my calculus students from last semester scored a goal in the national championship game, Christian Bain. So, all right. Can you see that down there? So, are you here? That's a clicker question. But first problem we're going to work on today is there's this integration problem. You have the natural log of 1 plus x squared times x. This I pulled out of the textbook, this problem. We'll do one that's not in the textbook in a second, but this is kind of an odd one for the textbook to give you because you can actually solve this. You can actually find the antiderivative. You can do a u substitution, you get the natural log of u. And how do you find, who remembers what technique we use to find the natural log, to integrate the natural log? By parts. And you pick the natural log of u to be your u. You take the derivative of the natural log, and you take the antiderivative of 1. And so it's kind of a trick there. So this one's one you can actually find the antiderivative of, but this technique is used mainly where you can't find the antiderivative. So go ahead and start, find the power series for this, then take the antiderivative of that power series term by term, and see how far you need to go to approximate the actual value to 6 decimal places. Okay? We'll talk about what that means, 6 decimal places, in a second, but why don't you guys get started with that? So I'm going to start working on it up here, okay? So if you need help, you can look up, but try to do as much as you can by yourself. All right. I tried to write out a lot. So first, let's talk about the error. So when the book says calculate it to 6 decimal places, what it means is it needs to be within, so I went out to my 6th decimal place, but it doesn't mean less than 0.000001, where that 1 is in the 6th decimal place. It means less than point, and you have 6 zeros and 5. So that means, the idea is if you're less than half of the 7th decimal place away, then if you round, you're going to end up with the 6th decimal place correct. So you go out to the 6th decimal place and then 5. Or you cut in half what it would be if this was a 1. If you went 0.000001, you cut this in half, and then you get this error. That's what it means when it says, that's what the book means when it says correct to the 6th decimal place. All right, so we need to calculate, so I started with this series right here. I knew that I could do things to this geometric series to get this. So I started with that. A lot of you already have the natural log of 1 plus x, that power series memorized. Great. Okay, but you should have it memorized for the exam. So you don't have to generate it from scratch. But I did this from scratch. So 1 over 1 minus x, it's this geometric series. And I first got it to 1 plus x, because here I have the 1 plus x squared. So I plugged in a negative x wherever there was an x, so it became alternating. And then I found the antiderivative of that to get the natural log of 1 plus x. So I know a lot of you probably started from here. I don't know about a lot of you, but then I replaced x became x squared, and then I multiplied by my x, and I finally had an expression for the x times the natural log of 1 plus x squared. But the problem wasn't to get that expression. Now we're going to use that to find the antiderivative of that and evaluate it from 0 to 0.2. So then I found the antiderivative term by term, and I plugged in 0.2. And if I plug in 0, what do I get? I get 0, because I don't have any constants. So you just end up getting minus 0. So I just have to focus on this first series. And how am I going to figure out that error now? How do I know how far out I have to take this sum? So the key part here is looking at, I should have written out one more sign. Look, we have an alternating series here. When we plug in 0.2, we still have an alternating series. So I can use the alternating series remainder theorem if it satisfies the alternating series test. Are these terms going to 0? Well, you can say yes, but how do you know for sure? Like the denominator gets larger, and the numerator gets smaller, so it's got to go to 0. So the terms are going to 0, and each term is smaller than the one before it for those same reasons. So the alternating series remainder theorem says we just have to go out to some term, and the sum up to that will be within that much of the true value. Okay? So if I take the first 3 terms, then I'm going to be within the 4th term of the true value. If I take the first 4th term, I'm going to be within the 5th term. So we need to find the first term that is less than what term is less than 0.0000005. Okay? Have you anyone tried punching these out on your calculator to see how big they are? Let's try this one. That's going to be 2 to the 8th over 10 to the 8th. That's my 0.2 times 8 times 3, or times 24. 10 to the 8th gets us at 0.000000001. So that 10 to the 8th gets us there. What's 2 to the 8th? 2 to the 5th is 32, 64, 128, 256. 256 divided by 24 is only going to be about 10. So we're only going to be about 10 higher than that. So we're going to be about 0.0000000, what's that? 1. We'll only be about that. And we're good. Because we just needed to be less than 0.0000005. So six zeros in the 5. We're at 6 zeros and a 1. So we're even better. So how much did we have to add up to be within that accuracy? Just the first 2. That's all we needed to add up. Just add up the first 2 factorial. I meant just 2. Okay. Any questions about this? Okay. Does anyone know what this integral represents? Population what? Nope. Could represent something from a population. It is an area under a bell curve. That's right. Nice job. Are you a stats major? You should be. All right. So this is the probability of being larger than average and less than 1 standard deviation in a normal distribution. So the bell curve, here's our average, looks something like this, where this will be 1 standard deviation up, this is 1 standard deviation down, so it represents this area. Okay. So I would like you to calculate what that value is to 2 decimal places. That's it. Okay? Use a similar technique that we just used and get me within 2 decimal places. If you haven't chimed in to say you're here, I'm going to be closing down the eye clicker in just a second because we're going to use it in a minute. So please chime in if you haven't. Okay. Yes. Were you just stretching? Oh, yeah. Okay. All right. So here's my work. I started off with e to the x because that's like the base function here. E to the negative x squared over 2. I'll take e to the x. I know the power series for that. And use that to find the power series for e to the next over 2. So everywhere there was an x up here, I plugged in a negative x squared over 2. And then I simplified it here. And now I use that to set up my integral. I'm trying to find the area under that curve, area under this curve, and this isn't something that we can actually find the antiderivative of. There's no elementary function that we could write down and take the derivative of and get e to the negative x squared over 2. It comes up a lot. The antiderivative of this comes up a lot, so much that it has a special name. It's called the error function. They shorten it to ERF, E-R-F. Yeah. So if in Wolfram Alpha you plugged this in and said integrate e to the negative x squared of 2 over 2 from like 0 to 1/2, in the answer it'll just say ERF of a half somewhere, like, yeah, for the error function. So we have to find some other way to find this area. So we do have other techniques. We could do numeric integration techniques, right? Use Simpson's rule, chop it up into 10 or 20 something intervals. This is another way. So we can just find the power series, and then term by term you find the antiderivative. So that's what I did. 1 becomes x squared over 2 becomes x cubed over 3 times 1/2, etc. So I just did the power rule for each of these, and then I evaluated it from 0 to 1. What's going to happen when I evaluate it at 0? Yep, I just get 0. Okay, there's no constants here. And so I plug in 1, and I get 1 over the square root of 2 pi times 1 minus a sixth plus 1/40th minus some other stuff. Now, luckily this is an alternating series. So for some of these integration problems, we pretty much only have like that. All of the problems the book gives you will produce an alternating series. So that's the error formula that we use. On these integration problems, there's other problems that we talked about last time, not last time, but last week, from 1110, where we can use Taylor's inequality to calculate errors. But for these, the book's nice, gives you alternating series. So we just have to go out far enough until one of the terms is less than, I asked for 0.0, I asked for 2 decimal places, so we need to find something that has less than 0.005. Okay? And that needs to include this one. Did someone go out far enough? Did you find one? So this one is the first one. Okay, so what is 1 over the square root of 2 pi 7 times 2 cubed times 3? What was that? Oh yeah, 3 factorial. Okay, so 0.0000187. Okay. 1187? Oh, great. Even smaller. All right. So that is less than, so 0.005. That's less than 0.005. So we only have to add up these first 3 terms. So, and that's enough. And did someone actually calculate what that is? So let me write this down. The integral of 1 over the square root of 2 pi e to the negative x squared over 2 dx from 0 to 1 is about 0.005. 0.132. It should be close to, it should be close to 0.34. So, all right. What do you get if you double this? Yes, Alex? Okay. So what do you get if you double that? 0.68. Now think back to your stats class. And why should that seem familiar? So the rule of thumb, with the amount of the population in a normally distributed with a normal distributed variable, about 2/3 or 67 or 68% of the population is within one standard deviation. We just went from one up, but if you go one down, it's symmetric, so we can just double it. Okay, we're going to test to see how close we are to normally distributed here, or fitting the normal distribution of height in the United States. So pull out your eye clickers. Anyone know the average height of a man in the U.S.? It's 70 inches, which is 5'10". Okay? Standard deviation is 3 inches. So for males, if you are between 67 inches and 73 inches, so that's 6'1". Well, the statistician would say it doesn't matter because the probability of being exactly on 67 inches high is 0. The problem with that is we kind of round, don't we? So we'll say, let's split the room. I'll tell you what you know. So we're going to split the room. So you behind Emily, you're on this side, okay? Here, if you're exactly on, don't include yourself. Here, if you're exactly on, okay? So females, the average height is 64 inches. Standard deviation is 3 inches. So you're down to 61 inches, which is 5'1". And we're up to 67 inches, which is 5'7". So if you are within that range, click A. And if you're not, click B. Oh, I didn't turn it on. No wonder it hadn't been. All right, try again. So if you are within that range, click A. If you're not, click B. If you're exactly on this side, what did we say? Include. Okay, don't include on that side. If you're exactly on one of those endpoints, include on this side. Yep, so if you're not within this range, I think, Christian, I think you're shorter. Are you wearing heels today? Is that what my wife is 5'2". And she was taller than her mother, and her mother's mother was taller, and her mother was taller than her mother's mother. So, my wife's grandma's 4'11" and 3/4. So. All right. So if we fit the distributions, or if you guys were randomly sampled from distribution, ideally, what should we end up with? For A's, 68%. We are at 75%. We are at 75%. So the question is, are we kind of high or low? So for those of you that did not click, okay, this is only for those of you that did not click. So if you're out, for those of you that are outside that range, so for those of you that clicked B, so for those of you that clicked B that are outside that range, click A if you're higher than that range, Click B if you were on the low side of things. Okay? And there, I just started another one. So click. So just for those of you that click B, okay, we want to know if we have people on the high end or the low end here. A, I said A if you're what? High. And so yeah, A if you're taller than one standard deviation. B if you are smaller. People are pressing C and E. I don't know what that means. On even days, you're taller than this, but on the other days, you're not. You do shrink. Yeah. All right. So what should we have if we were pretty close to normal? And our mean was 70 inches. I mean, our mean was respectively 70 and 64 inches. What should we have had in this result? It should be 50-50, right? About half the people that weren't in the standard deviation should be high. About half the people that weren't within one standard deviation should be low. 71% are high. So we seem to be pretty high here at BYU. It's pretty tall. This is for US. Yeah. Yeah, that's right. I mean, this is we have a little bit of a bias in the sample who's here, right? So these are the people that really love Brother Corey. They want to get every extra credit. I gave you just points for coming today, the quiz. So. All right. Okay. If you've got a device, I set up a quick Google form. Okay, that's supposed to say Corey Class Survey PS for Power Series. Just one question. It asks, what questions do you have about Power Series, and what do you not understand about Power Series? If there's anything. So.
Well, I have a question about what would you do if somebody found
Man. Okay. Well, I'll change that. I'll change that and send it out again. I was hoping to get some in real time, and then we could start talking about some of the questions. So here's the first question. So what do you get if you have like two bounds, right? The lower bound is 0, and what do you do? Well, you can calculate. One of them will be positive, one will be negative. So you can calculate both of those errors. Okay. What's your name? John. Okay, John. So you can plug in your upper bound. You can calculate, see how far you need with that error. You can do the lower bound also. You can fill out. That might be a little overkill because you get those things cancel out, right? But I haven't seen a problem like that yet. That's right. So that question, this is a good question. That question was when you differentiate, you lose a term, so your n equals 0, your index could change, but when you find the antiderivative, when you integrate, does it stay the same? It depends on the context. So when you take the derivative, you may or may not lose a term. I think last time we did like cosine of x. No, it wasn't cosine, it was sine. Because your first term is x, when you take the derivative, then that goes to cosine, but here you get 1 minus x squared over 2 factorial. So you don't lose, you may not lose a term. If you're trying to find a definite integral, like we were, then we're using the fundamental theorem of calculus here to find this integral. And the fundamental theorem of calculus says we can use any antiderivative. So we're going to pick the antiderivative with a constant of 0. So here we don't have to worry about finding a constant. But if we're trying to find, for example, the inverse tangent of x, which we could find by finding an antiderivative of 1 over 1 plus x squared dx. When we would have to find this power series, and then when we find the antiderivative, we would have to add a c and then solve for that c. So and the way you solve for it is you plug in your center. So inverse tangent of a equals whatever that is, and then you can say, okay, c has to equal whatever that is. So does that help? Okay. Other questions? Yes. I thought the easiest way was just to write out the first few terms and think about it that way. So you don't have to. You can think about what those first terms would be. If you haven't, like an n equals 0, x to the 2n plus 1 over, I don't know, n factorial. I don't know what this would be. But if you've got something like this and then you find the derivative, then you can think about, so you're going to have a 2n plus 1 x to the 2n over n factorial. What do I get if I plug in n equals 0 here? And what did I get when I had n equals 0 here? At n equals 0 up here, I had x over 0 factorial. At x equals 0 here, I just have 1 over 0 factorial times that constant, and that's what it would be. So it would not change here. So you can just think about, oh, my first term here, oh, it was an x, so I better have a constant still here. Hey, at n equals 0, that's where I get my constant. I'm still at n equals 0. Does that make sense? That's the kind of thinking you can do. Good question. Other questions? Okay. Little word of warning before we break. Our final is on the very first day of finals. So, and we don't have a lot of review. I don't think we have any review days scheduled in lecture. So what I'm telling you, we will have some review sessions. We'll set up some review sessions. On reading day, I'll probably have a 2-hour review session. But what I'm telling you is you should start now. We're basically 2.5 weeks away from the final exam, and you should start now reviewing, and especially that last week. You're going to be learning some new material. I made a mistake with the schedule this semester, and I should have put in some review days at the end. I apologize, but you're not going to have a lot of time to review if you wait till the last day of class and then plan on reviewing. You pretty much have one day. Yes? Yes. Yep, parametric curves and polar curves, there will be, I can guarantee you there's going to be at least one parametric problem, there's going to be at least one polar problem. Especially because it hasn't been on any of the other exams, they make sure they put it on there. Yes? No, it's the same like the first two midterms. Yeah. Right, yeah, they're all about the same length. So that question was, what's the composition of the final exam? It's about like your first two midterms. Some short answer, some 6, 7, 8 multiple choice, and then free response.
Have a great break.
Yes, it's on the If you go on Learning Suite, there's an announcement on our class to the right side that tells you exactly what it's going to be. Oh, where? They haven't sent that out. Sorry, I thought you said when.
We have 3 written assignments due on Monday, right?
On what?
On Monday we have 3 written assignments due.
I can't remember.
The one that was on Learning Suite is due today, is due Monday, right? And then there was 2 on Learning Suite that were also due Monday.
Yeah.
Yeah, that's one that's Tuesday.
Yeah. The TAs know better than me.
Thank you. Happy Thanksgiving.
You're welcome. Me too.
And there's one more midterm.
Oh, I forgot. You guys can stay for the soap film experiment that I emailed out. It's real soap. It's right over there in that bucket. So it's really cool. You can stay for 15 minutes in this next class. He's going to do a really cool soap film experiment. So didn't I email that out? Okay. I forgot to announce it again.
All 5 of us are going to be here to watch it.
You too. Thanks.